In this video, we're going to create a moment-axial force interaction diagram for the rectangular section shown. We're going to calculate several different points that are shown. So we'll calculate a zero moment point, a zero tension point where we have no tension in our bottom steel, the balance point where our steel yields as soon as or at the same time as our concrete crushes, the tension controlled point where the strain in our steel equals 0.005. Which is our tension controlled limit for ACI. The pure moment capacity when our axial force equals 0, and then our zero moment tension point, so our pure tension capacity. We're going to be using this rectangular section, which has a 20-inch height, a 12-inch width, and 3 number 9 bars on both faces. Our F prime C is 4 KSI, and we have grade 60 reinforcement, so our yield strength is 60 KSI. We can find our beta 1, which we'll need throughout the problem. So 0.85 minus 0.05 times 4 KSI minus 4 is just going to be equal to 0.85, which is less than 0.65, or sorry, greater than 0.65, so this will be our beta 1 for the problem. And by the end of the example, I want you to be able to calculate the moment capacity under any given axial load. We should be able to calculate the axial load capacity under any given moment, so working either way. We should be able to find the section strain, curvature, and stresses under any moment and axial load combination. And then finally, we'll be able to create a moment axial load plot for any given section. The first point that we're going to find is our pure compression point, the point when we have zero moment and pure compression in this section. We're going to assume here that we have a strain across the section equal to 0.003. This means that both our top and bottom steel have already yielded. And we're also going to assume that the stress, the maximum stress in our concrete will be 0.85 F prime C. We use this as it allows us to be consistent with our other points where we're using our rectangular stress block approximation. And it also is a good relation between the compressive strength of a cylinder and the in situ strength of a column. So the first thing that we need to do is we can either calculate our individual forces. So we have 3 forces, or we can put them together to find our total force N. So we'll find our N is equal to 0.85 times 4 KSI times our gross area, which in this case is 12 inches times 20 inches, minus our total area, which we have 6 number 9 bars, or total area of steel, so 6 number 9 bars, plus our 6 number 9 bars times our Fy, which was 60 KSI. We can find then that our N is going to be equal to 1,156 kips. So this is our axial load. We know that our moment here is 0. So we have our first point for our moment axial load interaction diagram. We can also see that we have no slope to our strain across our strain profile depth. So our curvature here is equal to 0. We can also find the plastic centroid of our section. And to do this, we sum our forces times the distance from the top to the center of the force, and then divide by the summation of all of our forces. So for that, we would need to find our individual force components. So 3 number 9 bars times 60 KSI would give us 180. Our top and bottom steel are equal. And then we would have 0.85 times 4 KSI times our 12 times 20 minus our area of our steel, which would give us a force component here of 795.6 kips. All right, so we have our three force components. We have our different lever arms, so we could calculate our Y bar P from the top. So we'll have our value here. So we'll have 180 kip times 17.5 inches, our lever arm, from the top to the center of our bottom steel, plus 795.6 kips times 10 inches, the depth from the top to the center of our rectangular cross section, plus 180 times 2.5 inches. And then we divide by our total force N, so 1156 kips, which is just the summation of our three forces. And we'll get the centroid equal to 10 inches. So note that if you have a symmetrical cross-section, so geometrically symmetrical, and your steel is symmetrical, then the plastic centroid will just be equal to the geometric centroid, which is mid-height for this rectangular section. Our next point is where we have zero tension in our bottom steel. So we have our strain in our bottom steel is equal to 0, and so our tension force here is equal to 0 kips. We know then that the neutral axis depth is just equal to D, which is equal to 17.5 inches. We can use this neutral axis depth then to find our compression steel strain, our compression steel stress, and our compression steel force, and then our concrete force components. So we'll start with our compression steel strain. We know that our epsilon S prime is going to be equal to 0.003 divided by 17.5 inches times 17.5 minus 2.5, which will give us a strain here equal to 0.00257. So this is greater than our yield strain for our steel. So we know we're yielded. So our compression steel stress is going to be 60 KSI. Then to find our force, we have our area of our compression steel times the stress in our compression steel, our top steel, and it's going to be equal to 180 kips. So then we can find our concrete force component. So it's going to be equal to 0.85 times beta 1, 0.85, times F prime C, 4 KSI, times C, 17.5 inches, and then times B, 12 inches. And we'll find then our compression component for our concrete, our compression force for our concrete equal to 607 kips. So our total axial force then, and again, we have no tension in our bottom steel, so our T sub S is equal to 0. So then our total axial force here is going to be equal to 180 plus 607 to give us an axial force here of 787 kips. So this will be our axial load for our MN interaction diagram. We'll next need to find our moment. And to find our moment, we're going to sum our moments about the plastic centroid or plastic neutral axis. And what this will allow us to do is to not include the external axial load on the column, since that's applied through the plastic neutral axis. So summing these moments, we have our lever arm times our top steel component, our lever arm times our compression component, and our lever arm times our tension component. So the first thing that we need to do is calculate our different lever arms. So we'll start by finding our concrete lever arm. So our YCC is going to be equal to our 10 inches minus our beta 1C, so 0.85 times 17.5 divided by 2. And this will be equal to 2.56 inches. We can then find our top steel and bottom steel lever arms. So our top steel lever arm is going to be equal to 10 minus 2.5, so 7.5 inches. And our bottom steel lever arm is equal to 17.5 minus 10, or 7.5 inches. So our steel doesn't move, so these two lever arms are going to be the same for all of our points on the moment axial load interaction diagram. The concrete stress block does change though, so this concrete lever arm will change. So on all of our next points, we'll need to recalculate that point. So then using these different forces and lever arms, we can calculate our moment. So our moment here is going to be equal to 7.5 times 180 plus 2.56 times 607 plus 7.5 times 0, which will give us a moment here of 2,900 kip inches. So this is our moment to complete our point. We can also find our ultimate curvature, which will just be 0.003 divided by C 17.5. So 0.003, the strain in our extreme compression fiber, C, the depth to our neutral axis, and our curvature, assuming small angles, just opposite over adjacent, is going to be equal to 1.71 times 10 to the negative fourth radians per inch. So this will be our curvature at this point. Our next point of interest is our balance point. And this is the point when our concrete crushes. So we have a top fiber compression strain of 0.003 at the same time that our steel yields, which gives where our bottom, or the strain in our bottom steel is equal to 0.0021, our yield strain. So then we can find our neutral axis depth, C, just based on similar triangles. So we can find our C to be equal to our D, 17.5, times 0.003 divided by 0.003 plus our yield strain 0.0021 or 00206. And we'll get our C to be equal to 10.4 inches. We can then use this neutral axis depth C again to find our compression steel strain. So 0.003 divided by 10.4 times 10.4 minus 2.5 will give us a strain of 0.00228, which is still greater than the yield strain, so we still have our top steel is still yielding. We can then find our compression component from our top steel. So 3 square inches times 60 KSI will give us 180. And then our concrete component, 0.85 times 0.85 times 4 KSI times our C, 10.4 times B, 12, which will give us a force component here of 360.7 kips. And we know that our steel is yielding, so our tension component is just AS times FY. So our TS here is just our 3 square inches times 60 KSI, which will be 180 kips. We can then sum all of our different components. So 180 plus 360.7 minus 180, because we're in tension, will give us an N of 360.7. So this will be the axial force component for our balance point. Next, we can use these forces and sum our moments about our plastic centroid again to find our moment. So we'd remember that our top and bottom steel lever arms are the same, so we don't need to recalculate those. But our compression lever arm is going to change as our compression block changes. So we'll have 10 inches minus 0.85, our beta 1, times C, which was 10.4, divided by 2, will give us a lever arm here of 5.6 inches. We can then plug all these lever arms with our forces into our moment expression to get a moment equal to 7.5 times 180 plus 5.6 times 360.7 plus 7.5 times 180 will give us a moment of 4,720 kip inches. We can then also calculate our curvature. So our curvature is going to be equal to 0.003 divided by 10.4, assuming small angles, and we'll get a curvature of 2.88 times 10 to the negative 4th radians per inch. And that gives us our moment and our curvature at our balance point. The next point that we're going to find is our tension control point. And this is when our concrete top fiber strain is 0.003, so our concrete crushes when our steel strain is equal to 0.005, which is our ACI tension controlled limit. So using similar triangles again, and a linear strain profile across the depth of the section, we can find our C. So our C is just going to be equal to 17.5 times 0.003 over 0.003 plus 0.005, which will be 3/8. So we'll get a C here of 6.56 inches. We can then use this C to find our compression steel strain. So our epsilon S prime is equal to 0.003 divided by 6.56 times 6.56 minus 2.5 will give us a strain here of 0.00189. So we're not yielded, so we need to find the stress in our top steel by taking our modulus times the strain that we just found to give us a stress value of 53.8 KSI. We then take this stress times our area of our steel, so 53.8 KSI times 3 square inches to give us our force component here of 161.5 kips. We can then find our concrete force component. So we have 0.85 times beta 1, 0.85 times F prime C times C times B will give us a concrete force component here of 227.5 kips. And then finally, our tension steel, we're still yielded, so our tension steel force isn't going to change, so we still have a tension steel force of 180 kips. We can find our total axial load then by summing these forces. So 161.5 plus 227.5 minus 180 will give us an N of 209 kips. So this will be our axial force for our tension control point. We can then use these forces and our C, our neutral axis depth, to find our moment and our curvature. So first, again, we need to find our concrete lever arm. So Y C sub C is just our 10 inches minus beta 1 times our C, 6.56 inches, all divided by 2. Which will give us a lever arm here of 7.2. And then finding our moment, we'll find our moment to be 7.5 inches times 161.5 plus 7.2 inches times 227.5 plus 7.5 inches times 180, which will give us a moment of 4,200 kip inches. And then we can find our curvature. So our curvature will be equal to 0.003 divided by our C, 6.56, which will give us a curvature of 4.6 times 10 to the negative fourth radians per inch. So then we have our curvature and our moment for this point. So the next point that we're going to look at is our pure bending point when our axial load is equal to 0 kips. this point, we don't know enough information from our strain diagram to be able to calculate C directly. Our strain and our tension steel is unknown, so we're going to need to start from our equilibrium expression, setting the summation of all of our forces equal to 0 to calculate our C, similar to what we would do in from our flexure section. So the first thing that we can do is calculate all of our force components in terms of C. And we'll start with our compression steel component, which will be equal to 0.003 times 3 square inches times 29,000 KSI times C minus 2.5 inches divided by C, which will give us a component equal to 261 times C minus 2.5 inches divided by C. We can then find our concrete component. So our C sub C is just going to be equal to 0.85 times our beta 1, 0.85 times F prime C, 4 KSI here, times C, unknown, and then times B, 12 inches, which will give us a concrete component of 34.68 C. Our tension steel, we know is yielded already, so this will just still be 180 kips, and it'll be independent of our C. So we can plug all these into our N expression, and we'll get N equals 261 times C minus 2.5 divided by C plus 34.68 C minus 180 equal to 0 kips. So we have no external applied load. We can simplify this into a quadratic, so multiplying through by C and then shifting some things around to get 34.68 C squared plus 81C minus 652.5 equal to 0 kips. And then solving for C, we'll get our C to be equal to 3.32 inches. So this is our C that we're going to use to calculate our forces and our lever arm and our moment on the next slide. Using our C, we can calculate our concrete force. So this will be equal to 34.68 times our C, which we found to be 3.32 inches, which will give us a force here equal to 115.1 kips. We can then find our concrete lever arm. So 10 inches minus 0.85 times 3.32 divided by 2 will give us our concrete lever arm equal to 8.59 inches. And then our top steel force which is equal to 261 times our C minus 2.5 divided by our C will give us a compression steel force of 64.5 kips. So then we have our force components. We have our lever arm, and we know the force components and lever arm for our bottom steel, so we can calculate our moment. And our moment's just going to be equal to 7.5 times 64.5 kips plus 8.59 times 115.1 kips plus 7.5 times 180 kips, which will give us a moment of 2,822 kip inches. We can find our curvature then, 0.003 divided by our C, to give us a curvature at this point of 9.04 times 10 to the negative fourth radians per inch. So this is our curvature and our moment at our pure bending point. The last point we're going to find is our pure tension point, and this is where we have no moment and pure axial tension on this section. Because we're in tension, our concrete is not going to contribute at all, so we only have our tension, our top steel and our bottom steel contributing to the force. We can just sum these forces and we'll find our N to be equal to 6 total bars, all yielded to give us a force here of 360 kips. And we know at this point that we don't have any moment. So this is our force and moment for our next point. We also know that we don't have any curvature at this point because there's no slope to our strain diagram. So our curvature is also equal to 0. Here is a summary of all of our different points that we found so far. So our 0 moment, our 0 tension, our balance point, tension controlled point, pure moment, and 0 moment tension. And you can also see how the curvature increases as we decrease our axial load. So we'll look at in other examples how we can create a simpler moment-axial load interaction diagram, but our key points will typically be our 0 moment point, our balance point, our tension controlled point, and our 0 moment tension point. And we can also find our pure moment point if we want a fifth point. We can next find our curvature ductility at several different points. We'll find it at several different points. The three easy points to find are our pure compression, our balance point, and our pure tension point. In pure compression, we don't have any curvature, so our phi ultimate is going to equal 0, and our phi y will equal 0. So their phi ultimate and phi y are equal to each other. We can say, since we can't divide by 0 mathematically, we'll just say that our curvatures are very small, and then our curvature ductility will be equal to phi ultimate divided by phi y, which are equal, so it'll be equal to 1. With our balance point, by definition, our balance point is our steel yields when we reach ultimate. So our ultimate curvature is equal to our yield curvature. So here, our curvature ductility is going to be equal to 1. And finally, similar to pure compression, pure tension, we don't have any curvature in the section because we don't have any moment. So our ultimate curvature is equal to our yield curvature is equal to 0. And again, we'll say that our curvatures are very small rather than equal to 0 so that we can divide by our phi y. And we'll again find our curvature ductility here to equal 1. To find our curvature ductility at the pure bending point, we need to find our yield curvature first. So we know our ultimate curvature from our or from earlier in the example, and now we need to find our yield curvature. To do that, we need to first find our cracked transform section properties. So we can either do that from equilibrium, or because P is equal to 0, we can also do it with our simplified summation of our areas above and below times, or above times the distance to the neutral axis above equals to the same on the tension side. So when our P is equal to 0, these are equivalent. So what we can do is simplify this down into this expression, which is just a quadratic with our A, B, and C components. If we plug in all of our known values, we'll get 6 kd squared plus 45.6 kd, and then minus 478.5 is going to be equal to 0. And we can solve for kd, and we'll get our kd to be equal to 5.91 inches. So then we'll use this kd to find our yield curvature on the next slide. Using this kd, we can calculate our yield curvature because we know the strain now at the location of our tension steel. So we'll have our yield curvature is equal to Fy 60 ksi divided by 29,000 divided by our D 17.5 minus our KD 5.91. So we'll get our yield curvature here to be equal to 1.79 times 10 to the negative 4th radians per inch. Then we can calculate our curvature ductility just by taking our ultimate curvature, 9.04 times 10 to the negative 4th radians per inch, divided by our yield curvature, 1.79 times 10 to the negative 4th radians per inch, to give us our curvature ductility of 5.05 at this point. So we'll plot this point for our final curvature ductility plot. We can find additional points for our curvature ductility plot and also for our moment curvature plot just by plugging in different values for n in our equilibrium expression. So we're going to find an additional point where we have 300 kips in tension applied to our column. And we'll sum all of our different force components and set it equal to negative 300 because that's tension for us. So our C S prime component, we're going to put in terms of C, our neutral axis depth. And we did this math on a previous slide, so we can just plug in directly, and we'll have 261 times C minus D prime divided by C is going to equal our compression steel force. Our concrete force, again, we did this earlier, so our compression steel force is just going to be equal to 34.68 times C. And our tension steel force is equal to 180 kips because our steel is yielded. So then we can plug all these in to our total axial force expression, and we'll get 261 times C minus 2.5 divided by C plus 34.68 times C minus 180 is going to equal negative 300 kips. If we simplify this into a quadratic, we'll get 34.68 C squared plus 381 C minus 652.5 is going to equal 0. And then we'll get our C equal to 1.51 inches. And we'll use this C moving forward to find our nominal curvature and our nominal moment capacity for this point. Using the C that we found on the previous slide, we can calculate our compression force component, which here will just be 52.2. Our lever arm, which for us is going to be 9.4 here. And then our top steel force. So plugging in our C of 1.51 is going to give us a compression steel force component of negative 172.2. We can see it's negative, so it's actually going to be a tension force. But we'll plug it in with our negative sign, and it'll kind of take care of itself. So plugging all these values in for our moment, we'll find our moment to be 7.5 inches times negative 172.2 kips. So our compression steel component is going in the opposite direction now because we're in tension. So it's going in the opposite direction of our tension steel and our concrete compression forces. So that's why we have a negative sign there. Then we'll have plus 9.4 inches times 52.2 kips plus 7.5 inches times 180 kips will give us a moment here of 547.1 kip inches. So this is our moment. And then we can also find our curvature, which will just be equal to 0.003 divided by our C, 1.51, which will be 19.9 times 10 to the negative 4th radians per inch. and this is our ultimate curvature. We're next going to find our yield curvature. And to find our yield curvature, we need to find the depth of our neutral axis using our cracked transform section properties. We're going to start from equilibrium here to find the depth of our neutral axis KD because we do have an axial load that's being applied. So we have our concrete, steel, and tension force components related to the strains. We plug in our different strain values to get everything with respect to steel strain, epsilon s, and then plug in all of our known values to get our equation in terms of just KD as a quadratic, and then we can solve for KD. And here we see that our KD is actually negative, so our KD falls above the cross-section. So that means that the entire section is going to be in tension. Because the entire section is in tension, we need to neglect the concrete component. So because this is negative, we're going to take out our concrete compression force, and we'll only have compression steel and tension steel contributing to the overall force in our column. On this slide, we take out our compression force component. So we just have our top steel and bottom steel in our equilibrium expression. And this is because our compression component is equal to 0 because the entire section is in tension. So we can do the same thing as we did before, put everything in terms of epsilon s, and then put everything in terms of KD. And if we solve for KD, we'll get our KD to be equal to negative 27.5 inches. So this means that our neutral axis is 27.5 inches above the cross section, which means the entire cross section is going to be in tension. We can use this to find our yield curvature, and then use our yield curvature and our ultimate curvature to find our curvature ductility. And you can see that at this point we have a very large curvature ductility. So as we approach our pure tension axial load capacity, our curvature ductility is going to progress towards infinity. So here we plot all of our different curvature ductilities versus our axial load. And on the right side and on the left side, we're plotting our moment versus axial load. So you can see that we start off with a curvature ductility of 1 until we pass our balance point. And after our balance point, our curvature ductility progresses towards infinity, and up until we reach our pure tension capacity when we're back at 1. So if we were to plot more points, we'd get a smoother shape, and down below is more or less what our curvature ductility versus axial load plot would look like for a given column. And that concludes our example problem.